All right, welcome back to Math 160. We are going to continue in Chapter 6, Normal Probability Distributions. So last class, we had an opportunity to finally use the z-score table. So please separate that from your packet. You want to have that handy. We're going to use that quite a bit, of course, because we're still working with the normal distribution. We're still looking at the area under the curve, which is the same as probability, right? And then we can, of course, turn that into a percentage. Good. So let's pick up where we left off, which was on page, let me find this. We are on page 7. So turn to page 7. We're looking at the bottom. And you may want to have some sort of, coloring utensils so you can shade in the appropriate region. It's nice to have that visual, something that won't bleed through the notes, of course. All right, let's do it. Okay, so we were trying to find the z-score associated with a percentile, and we found that, sorry, my dog is walking like under the tripod of the camera, so I apologize for all the shakes. So we were trying to figure out for the first one, the z-score that's associated with the 85th percentile. We learned that 85th percentile means 85% of the population, right? So essentially we know that it was to the right of our mean because we know what that looks like, the area under the curve, that's 85%. And then we had to go to the table and figure out what z-score it was closest to. So when we actually examined the z-score table, we saw that our 0.8500 was in between these two values, which referred to a z-score of 1.03 and 1.04. So we had to say, okay, which one is it closer to? And we noticed that 0.8500 was definitely closer to 0.8508 instead of 0.8485. So we choose the one that it's closest to. So let's do that again. And we're going to find the z-score that is associated with the 24th percentile of a normal distribution. Let's go through the same process. We know the 24th percentile refers to 24%, right? We're outperforming 24% of the population. One of the things we want to keep in mind is that if we were to shade all the way to the middle, that would represent 50% of the data. But the issue is we want 24. So can we already have like some sort of guess as to where that would lie? I would imagine it's going to be possibly between maybe a -2 and a -1 for a z-score. So we're trying to guess how much would represent 24%. If we knew that if we shaded all the way to 0, that's 50%. So it's somewhere in here, I would imagine. But let's check it out. We're going to turn this 24% into a decimal, 0.2400. And now what we're going to do is, because we kind of have an idea that it's going to be on the negative side of our z-score table, let's go ahead and find 0.2400 or as close to it on this side of our z-score table. So the side that has our negative values. So let's go ahead and scope things out. We're looking for 0.2400. Does anyone see where that might lie?
Is it 0, 0?
0.07?
0.0 is all the way down here. 0.07 is approximately here.
No, I meant 0.7. Sorry, I misspoke.
No, that's okay. Okay, beautiful. So -0.7. And then notice 0.2400 is somewhere between these two values. So if it helps, I'm just going to write that in here, 0.2400. And now we have to decide, is it closer, 0.2400, is that closer to 0.24196 or to 0.23885? How can I figure that out?
Subtract.
Yeah, let's do it. Let's take the 0.24196 and I'm going to subtract the 0.2400. Okay, so that difference is 0.00196. So that's something to think about. And it might be worthwhile writing down. That way we're like, that way we're not wondering what What was that value? What was the difference? So our z-scores, again, are negative 0.70 and negative 0.71. So I'm going to write those as my options. So the area for the 24th percentile lies between a z-score of negative 0.70 and negative 0.71. It would be helpful to write what those areas are for each one. We notice the area to the left of a z-score of negative 0.70, that's 0.24196. The area to the left of a z-score of negative 0.71 is 0.23885. So we have to figure out, like I said, which one it's closest to. When we subtracted these, we saw that the area was the difference in areas was 0.00196. Let's look at the difference in areas between these two. So we're going to punch in 0.2400, since that's a larger amount, minus 0.23885. And that gives us 0.00115. So just by looking at the difference, we see clearly that we are actually closer to negative 0.71. So we are closer to z is equal to negative 0.71. And that is your associated z-score. When we plot this in negative 0.71, so we're pretty close to that negative 1, but not quite. We'll draw our dotted line up. We'll shade the region, of course, just like we did last time. And we know that this region is approximately 24%, which is what we were looking for. So it's approximately 24%. What's on your mind? Talk to me. What questions do you have about this?
I have a question because I was writing. I didn't see what you subtracted when you did your subtraction.
So what I ended up doing was I wrote down below each z-score what their respective areas were, because we know we're trying to figure out which one we're closest to.
Yeah.
So in order to figure out the distance from 2400, I just subtracted these values to figure out that separation. And then I subtracted these values to find that separation.
Okay. Oh, so you subtracted both from 2400.
Yeah, because I wanted to see which one was closer. Just be really careful. You always want to do larger number minus smaller number because distance is positive. But yes, that's exactly right.
Okay, thank you.
You're very welcome.
How did you get negative 0.70 and negative 0.71?
What I ended up doing was, because I'm looking for this area, 0.2400, I went to the, and I apologize, I'm going to cover this for a second. I went to the negative side of my z-score table and I was scoping out all of these areas until I found 0.2400. And I got pretty close, but I couldn't hit exactly 0.2400 because that's not an area listed on this chart. So we see that 0.2400 sits between these two areas, which represent a z-score of negative 0.70. And then this area, which is a negative 0.71. Does that help?
Yeah.
Awesome. Awesome. Because you want to find the 24th percentile, you convert that to a decimal. That is your area. So the area is all of these values in the chart themselves. The associated value would represent its z-score. So as you see here, These are all your z-scores. This is for your ones in your tenths place, and then this is the hundredths place of that particular z-score. Good. Any other questions?
Can you go back? I just want to see something.
Yes.
How did you get the z-score says like negative 0.70 and negative 0.71, right? So how did you get like negative? I mean, I understand the first one, but how did you get the second one? Negative 0.71, because I thought it was supposed to be like 1. No,
So
0.01 is not.
no. So the areas here refer to, okay, so think of it this way. We want to know where the z-score lies to account for an area of 24% under the curve, right? An area of 0.2400. So are you okay with the fact that we found these two z-scores? Is that part okay?
No.
Oh, okay. So I'm just going to explain that one more time. Do you see here, Donna, that 0.2400 sits directly between these two values?
Mm-hmm.
It does, right? So 2400 sits between 24,196 and 23,885. So we see exactly where that 0.2400 sits. Now, when you think about this, let me highlight these values because that might be helpful. We're looking at these two areas that have corresponding z-scores. So what we do now is we say, well, what is the z-score for this first value, this first highlighted area? So the z-score associated with this one is negative 0.70.
Okay.
That's the first z-score. The second z-score is negative 0.71.
Oh, okay.
Right?
I see now.
Beautiful. That's where we're getting those z-scores from, but these are their areas. So what I like to do directly is I will write down the z-scores and their associated areas. You see how I wrote it directly underneath?
Yeah, I see now.
Good. We know 2400 is somewhere in between, and then we just have to say, which one am I closest to? So I subtracted to figure that out. Which one am I closest to?
So the 0.00196 will be the closer one.
Look at these two values. So we have 0.0019, 0.0011, right?
Okay.
This is a smaller value than this one. So we're closer to 0.23885. You're going to compare these. Yeah, when you think about in terms of, decimal placement, if you were to line these up, you would say this 0.00196 is a larger value than 0.00115, right?
Okay, yeah, true. Okay.
And you
Yeah.
just go, place by place, 001, because this one's a 9 and this one's a 1, this is a smaller distance, which means it's closer to this value.
Okay, I see now.
Yes, beautiful. You always want to look at which one it's closest to. Same thing with our previous example. Notice we wanted to figure out where 8500 was with respect to these two values, which one it's closer to. And pretty immediately we were like, oh my gosh, it's so close to this value, right? Versus the other one. So that's essentially what we did. We subtracted to see which one it was closer to. Fortunately for us, it was super, super visible that it's closest to 0.8508, right? Versus 0.8485. Does that help?
Yes.
Sure. All right. Very, very nice. Let's turn the page. Okay. Finding the z-score when given the area under the standard normal curve. So this is the exact same idea, except we don't have to turn 24th percentile into 0.24. We're actually given the area. So it's the exact same process. If the area under the standard normal curve to the left of a z-score is 0.6554, find the associated z-score. Question, if you had to guess where might our z-score be if the area to the left is 0.6554? Take a guess.
In between 0 and 1.
Yeah, I love it. I think that's a fantastic guess. Yes, Abby says positive. I actually really love that. Regardless of whether you're saying specifically between 0 or 1, or noticing that it's got to be on the positive side because only 50% of the data is to the left of 0. So we have to shade more, right? So we recognize that we're on the positive side. So let's go to the positive side of our z-score table. We're looking for 0.6554. So I want you all to investigate this side of your chart and find exactly 0.6554. Yes, Abby. Jenny.
0.40. Oh,
Yes, yes, I love it. 0.40. Beautiful. I'm going to highlight that. 0.6554 is right here. That refers to a z-score of 0.40. The cool thing is we didn't have to worry about finding in between values. Boom, there it is.
Wait, I don't get it.
So these values are all the areas under the curve, and the question asks us to find the area, to find the z-score that's associated with an area of 0.6554, right? So if this is the area, I'm going to write this down.
Oh, okay. I get what you're saying now.
Beautiful. And you just look it up in here. These are all areas. My advice to all of you, once you find it, highlight it. Because then you could say, this is a value I'm looking for, and its z-score is 0.40, right? 1/10, 100th place.
So I have a question.
Yeah.
If we convert the 0.6554 into a percentage, would that be like 65%?
It would be 65.54%. Yep, exactly.
Mm.
That's
are these all the areas still left of the,
yes.
can we write that down on there so that we,
Yeah. Areas to the left. I don't know why I wrote it that way. My brain literally wrote it that way. Wasn't that weird?
We'll just blame it's a Wednesday.
I think honestly though, that's pretty common for me. Like if I'm thinking about something and someone's like with me, we're hanging out, sometimes I'll tell them half the story because the first half I had in my head. It is so weird. I don't know why that happens. Okay, so areas, these all represent the areas to the left of the z-scores, just like on the other side, same thing. They represent the areas to the left of the z-score. Good. So we see our z-score is 0.40. So let's write that down. Z is equal to 0.40. We knew to expect that. So we're approximately here. Draw your dotted line up. And of course, shade the appropriate region. So we are referring to all of this space. So when Donna said, is 0.6554 the same as 65%? And the answer is yes, because look at this area. This is approximately 65% of the population falls within this range. And you know that's a pretty good estimate because up to 0 is 50%. So anything more obviously is going to be more than 50. Let's do it again. This time, let's trip you up a little bit. If the area under the standard normal curve to the right of a z-score is 0.7088. This is interesting. Find the associated z-score. So I want you to think about this for a moment. The area to the right is 0.7088. Where would we be if you had to guess?
Between 1 and 2.
So if we were between 1 and 2, and I put a point here, for instance, and I shaded this region to the right, is this region to the right going to be 70% of the data?
No.
No, so this one's tricky because this one's actually saying to the right of the z-score is 70.88. Where
Don't
else?
you have to subtract it from 1?
Okay, I love where your head's at. So first things first, Kelly's noticing that if we want to find the area to the left, we have to subtract from 1, and we are going to do that. But before we actually go through that process, I just want you to take a second and tell me where you think that particular z-score is going to be located.
Between 0 and -1.
Ah, so somewhere over here. I like it. I like it. That's a really good guess. Because if we plotted our point here, drew a dotted line up and then shaded, we see that that's definitely more than 50% of the data. So that could be around 70% of the data. So let's take steps to help us. Since the z-score tables provide the area to the left, we will subtract our area from 1 to give us the area to the left. So the area to the left is going to be found by taking 1 minus 0.7088. So let's go ahead and punch that into our calculators. What do you get for the area to the left?
0.2912.
Perfect. 0.2912. Our guess was that it's going to be somewhere here on the negative side, which I love. So let's go to the negative side of our z-score table. Now, don't say this out loud. I want everyone to actually have an opportunity to do this. So look on the negative side of your z-score table, and you're looking for an area of 0.2912. In the chat, please send to me privately what the associated z-score might be. 0.2912. I'm going to highlight it on mine as well. Anthony, excellent. Sam, excellent. Thank you for sending that to me directly too. We're looking for 0.2912. Give me the associated z-score. Let's look for 8 more answers in the chat. That will give us a total of 10. Emma, thank you. Perfect. No, Anthony, it's not a coincidence. And I'll explain that in a second. It's because it's symmetric. So I love that you were looking at that and you're like, holy crap. But we know it's got to be the negative side. Nick, excellent. Nicole, what's the associated z-score for that value? Kelly, get rid of that get rid of the 0 between the 2 5s. That's got to go. But yes, you'll be good. Donna, you're missing 1 more place after the decimal. Grace, Nicole, excellent. Jenny, Nicole, that should be negative. Jenny, you're missing 1 place after the decimal. There should be 2 places. Mike, excellent. That's okay. Yes, Nicole, perfect. 1 more. 1 more answer in the chat. Not quite 0. Donna, try that again. Highlight the value itself and then see which column it's in. That's going to help. 1 more answer.
Oh, I see.
Good. It would be that, yeah, it would be that value at the end. So put those answers together and you'll be all set. All right, check it out. Let's go to the, thank you, Holly. So 0.2912 is actually right here, right? 0.2912 is practically this value. It was just rounded to the tens, hundreds, thousands, 10,000s place as opposed to the 100,000s place. So 0.2912 is this particular value, which I highlighted. This has an associated z-score of negative 0.55. It's not 0.5. Think of it like this. Your negative 0.5 is the first part of the z-score. That 0.05 is the rest. So when you combine those together, and you're just looking at this in the positive sense, it'll give you 0.55. And then of course, keep that negative sign. I hope that helps. So negative 0.55 is the associated z-score. Good, very, very nice. If we plotted that point, negative 0.55, which is about here, we draw our dotted line up. And we are told the area to the right is 0.7088. So we're going to shade the area to the right, because this is the region being referenced right now. What questions do you have?
Professor,
Yes.
I have a question. So how do we find 0.2912 from this distribution list from like lot faster?
Well, I mean, I don't know how to, describe a lot faster, but essentially, that on the negative side of the table, your values will run from as close to 0, an area under the curve, and then up to, as close to 0.5000, right? Because that's halfway, that's half the data, that's half the curve. So that 0.2912 is definitely going to be on this side. Then I would just say, start looking at the values, right? Start looking at the values here and just see where 0.29 is. We start noticing we're in these 3 values, and then we think about, let's get closer, 0.2912. 0.2912 is going to be exactly this value, okay? Notice to the left or to the right, it wouldn't make sense to look at either of these values because this is essentially 0.2912. It was just rounded as opposed to having 5 places. Does that kind of help?
Yeah.
Okay, all right. We're going to keep doing this. We're not done with this idea. So I want you to still think about this in your minds. What I'm going to do now is introduce you to another notation, and that is z sub alpha. So let's look at this. The expression z sub alpha, do you see how it's a little and it's a subscript and it's to the right of z below? That's an interesting location for this. So this denotes the z-score with an area of alpha to its right. So if alpha is the area to the right of that z-score, isn't 0.7088 the area to the right of that z-score? Interesting. So I can actually write this as, let's say we were looking for the z-score that had an area to the right under the curve of 0.7088. That's actually how we would write this problem using this notation. So if I wrote to you, what is the associated z-score if you were told that, if you were given z sub 0.7088? Well, we have to say to ourselves right then, just by looking at this, is that we are looking for a z-score with an area to the right. Notice it's on the right, with an area to the right of 0.7088. That's what that says. That's what this notation means. It's on the right specifically. Also notice it's a subscript, so it's kind of like below, it's under z kind of. So the area under the curve to the right. Hopefully all of that is making sense to you, and you can kind of think about it in that way so that you never forget. You're like, oh, here it is. It's to the right. It's under the z. Okay, so under the curve, the area to the right under the curve. Okay. So for instance, if I wanted to find z of 0.10, let me illustrate that to you in a drawing because I think that's going to be helpful. So if we drew our normal curve, and I know I had almost all of them drawn, but I do want to show this to you because I find the visuals always help. If we want to find z sub 0.10, z sub 0.10, that means the area to the right of this z-score is 10%, which means the area to the left is 90%. So I would guess it's probably somewhere over here, right? Possibly. So what we're going to do is we're going to say to ourselves, well, if the area to the right is 10%, then the area to the left is 90%, so 0.90. Notice that I've written this out. We are looking for the z-score whose area to the right is 0.10. So just like Kelly suggested for number 2, we're going to subtract that from 1 and then look at the table. So 0.90. I just want to show this to you. If we go to the positive side of our table, we're looking for 0.90 exactly. Notice that with 0.90, let's take a look. We're getting closer, we're getting closer. Here we see 0.90 sits somewhere between these two values. I'm going to write 0.90 in between. And then we have to figure out which one it is closest to. We're going to do that same exact idea, or we could just kind of look at this and decide which one it's closer to. Is 0.90 closer to 0.8997 or to 0.9015? What do you think?
0.8997.
Yeah, for sure. It's much closer to 0.8997. When you subtract, you'll see the difference here is much smaller than the difference between these two. So I'm going to highlight the value that we're taking because we see that 0.90 is closer to this area, which has a z-score of 1.28. It's a z-score of 1.28. So if we go back to our notes, notice we were provided with that z-score, 1.28. So we were approximately here. So when we drew this dotted line up and we shaded the region it was asking for, we know that this region here is approximately 10% or approximately 0.10, which means the region to the left is approximately 0.90. So let's look at number 2. I want to find z sub 0.04. What is the area to the left of the z-score going to be?
0.96.
Perfect. Yes, 0.96. So I'm going to make a note here. If the area to the right of the z-score is 0.04, then the area to the left is 0.96. The area to the left is 0.96. Talk to me.
How did you get 0.96?
You always subtract your area from 1. So your total area under the curve is always 1 because think of probability, right? What is the likelihood that something happens all the time? Well, the probability is 1. It's like saying, hey, what are the chances that in that standard deck of cards, you pick a black card or a red card? You're going to be like, all the time. Why would you even ask that question? That's going to happen all the time. And then you would say the probability is 1 because it's always going to happen. So if you shaded the entire curve, all this region underneath this normal curve, that would be a total probability of 1. That would be if everything is shaded. So if you know the area to the right is 0.04, then what's left over is going to be the area to the left. This is why we subtract from 1.
I have a question.
Yeah.
So do you subtract from 1 when you're finding for the left alone or when you're finding for the right as well?
So for these particular examples, because the table always provides to us the area to the left, if we're ever provided the area to the right, we always want to subtract from 1. And it's literally because of the fact that these values always just give you the area to the left. So yes, this is why we subtract from 1.
Okay, thank you.
You're welcome. Also notice we didn't have to subtract from 1 here because we wanted the z-score, which had an area to the left of 0.6554. So we literally just found that area on the table as is. But when we want the z-score with an area to the right, that's when things get just a tiny, there's just one extra step. When we want to subtract from 1 to figure out the area to the left, that way we can use the table. All right. So let's actually use this information. So if we want to find the z-score, whose area to the left is 0.96, am I going to be on the negative z-score side or the positive z-score side?
Positive.
Definitely positive. So let's check this out. We're looking for 0.96. So I'm going to scope this out. My eyes are drawn to this region here. So 0.96 sits somewhere in between these two values. So I'm going to write 0.96 here. Which value is it closer to, the left or the right?
Left.
Definitely the left. Let's highlight this value. Right? 0.96 is super close to 0.9599. It's closer than to 0.9608. What is the z-score associated with this area? Donna. Mike, excellent job in the chat. Donna, what is the associated z-score with this area?
Oh, are you talking to me? I'm sorry.
That's okay.
Would it be 1.7 and then also 0.05 and 0.06?
So we want just this value right
Okay,
here.
so that would be like 0.05, right?
That is the hundredths place, but now put these two numbers together. What's the z?
That would be 1.16.
No, 1 point. Read it together. Read this. 1 point.
1.7.
And then 5. Finish it with the 5. So this is the hundredths place of the z-score. You don't keep that 0 there.
Okay, so you do 1.07 and then remove the 0 and just put 5.
I'm going to actually put these two together because I'm going to show you what this looks like. So I want you to combine these two together. So that's going to be 1.7. Directly underneath it, I want you to write 0.05. And when you add these, look at the value you get, 1.75.
Oh, okay, I see.
Right? So this is the ones, the tenths place, and here's the hundredths place. You're not keeping the 0 in the answer, right? Because when you combine those two, it gives you the ones, the tenths, the hundredths place, 1.75. Does that make more sense?
Yes.
Score. Excellent, Nick. Thank you so much for that response in the chat as well. So our associated z-score is 1.75. And you're done. We found the associated z-score. If we drew a little visual again, you're welcome to do this. You don't have to if you don't want to, but visuals tend to help. We're essentially saying that we know the area to the right is 4%. So that's like this area right here. That's 4%, which means the area to the left is 96%, right? Or 0.96. So I'm going to write here that the area to the right was 0.04. The area to the left is 0.96. And that's what we were looking for since our table provides us the areas to the left of the z-score. Keep in mind, I am recording this. So if you are trying this at home and you're like, shoot, I'm not understanding this, I need to hear this again, you have access to the video at all times. I would highly advise that you rewatch the video so that you can hear the language that is associated with this problem, so that you can hear how we break it down. Maybe watching it again without writing is going to be really, really helpful to you, but I want you to really take that time and invest in yourself, okay? Think about rewatching this if you need to. And remember, you can fast forward, you can rewind, you can pause, you can do all sorts of great stuff. So make sure that you're taking advantage of that. I'm putting them on Lumen for you every time so that you have access at any time. You know, maybe a week will go by and you're like, shoot, I forgot how to do these. You have the video, okay? You know what page this is on. That's what you're looking for, okay? Don't forget that you have that option. That's a definite success strategy. Awesome. Any other questions for me before we move on? Okay, turn the page. And let's take a look at these notes. Leah, would you go ahead and read the notes for these notes 1 and 2? Would you do that for us, Leah?
Yep.
Thank you.
If the desired value is midway between the two table values, average the two z-scores. For z-scores above 3.49, we can use 0.9999 as an approximation of the cumulative area from the left. For z-scores below negative 3.49, we can use 0.0001 as an approximation of the cumulative area from the left.
Cool. So just to kind of comment on this part, because this one can be tricky, you are actually able to have z-scores that are larger than 3.49. But if you look at your table, check this out. If you look at your table, the highest that this table goes is 3.49, right? Which has an area to the left of 0.9998. So what this is saying, and we can write this on our z-score table because I think this will be helpful. For any z-scores larger than z is equal to 3.49, we will state that the area to the left is 0.9999. I want you to write this on the positive side of your z-score table. For any z-scores larger than 3.49, we're going to state that the area to the left is 0.9999. We can't say it's 1 because, as you know, the tails never actually hit that horizontal axis. So it's not like it's a closed curve. It really does continue on for infinity. So we get as close to 1 as possible, which is why we'll simply write the area as 0.9999. So as close to 1 as possible, but it's not going to equal 1 exactly. Would you flip to the other side when you're ready? Because I want to look at the negative side and write another note. I'm switching this. Hopefully that's okay. notice here, the smallest z-score on this side is negative 3.99. But what happens if we have a score that's smaller than this? So let's write that down at the bottom. For any z-score smaller than z is equal to negative 3.99. So for any z-score smaller than a z is equal to negative 3.99, the area to the left will be, oops, will be approximately 0.0001. So 3 zeros, then a 1. That's the approximation. That's what we'll use if we ever see a z-score smaller than negative 3.99. Like, what if you got a z-score of negative 6? You're going to say, well, according to what I've written here, the area to the left is going to be 0.0001. We're never going to say that the area to the left is 0. Good. All right. Let's try some applications here. Kelly, would you go ahead and read part A for Introduction to Standardizing X Values?
Sure. There are many normal distributions with different means and different standard deviations, but there is only one table given for finding probabilities. The z-score table where the mean equals 0 and the standard deviation equals 1. What we need to do for each particular normal distribution problem is to put it into standardized normal form so that we can use the z-score table to find probabilities.
Yes, excellent. To standardize a problem, we use the standard score Z with the following formula. Quick question, what does that mu symbol represent? Anyone could shout it out. What does that mu symbol represent?
Mean.
Yes, the mean. What does this sigma represent?
Standard
Standard
deviation.
Yes, standard deviation. I love it. What does X represent?
Raw data value.
Yes, raw data value. Excellent. Notice there's a little cheat sheet here. In other words, the z-score is equal to the difference of the raw data value X and the mean, all divided by the standard deviation. We know that that is the same for, so this is the formula for a population. We know it's essentially the same for a sample, X minus X bar over S, but the formula is identical. It doesn't change. It's just the raw data minus the mean divided by standard deviation. Excellent. Let me show you what I mean. Statistics final exam scores are approximately normally distributed with a mean of 68. So right away, as soon as I see this, I'm going to write mu is equal to 68. I'm assuming this is a population because we're looking at the statistics final exam scores. We're not told that it's a sample, right? We're not told that it's from one class. We're just said generally statistics final exam scores. By the way, we know the formula is the same regardless of which notation you use. So don't panic if you're not sure whether or not to use mu or X bar. It's the same formula. And a standard deviation of 5 points. So right away, I'm going to write that sigma is 5. So we want to find the probability. Now, I'm going to help you to read this. These values, 65 and 75, these are not z-scores. We know this because of the letter that's in between. This letter represents the raw data value. Specifically, X in this case represents a statistics final exam score. That represents the X value. That's what that means. So we want to know, what are the chances that a student will score between a 65 and a 75? So the first thing we're gonna do here is we have to standardize those scores. We gotta give them a z-score. So I'm gonna write that down. First, we find the z-scores for each raw value, 65 and 75. So that means we have to find two separate z-scores. That's the first thing we do. And I'm writing this in steps so that way when you try these problems on your own, you can look back and say, okay, this is what we did first, and then et cetera, et cetera. So our first our first raw value is going to be 65. So that means we have no idea what z is. We do know that x, according to the formula that comes before the mean, we know that x in this case is going to be 65. We subtract the mean, which is 68. And we divide it by the standard deviation, which is 5. So when x, our statistics final exam score is 65, we see that the z-score is, let's go ahead and punch this in. Remember that when you state the z-score, you want to say it to 2 places after the decimal. Okay, so what is my z-score in this case? When you do the math.
Negative 0.6.
Yep, and add a 0 right after. So we want 2 places after the decimal. So we'll just tack on that 0. Nicholas, that's perfect. So negative 0.6, add the 0 at the end. It's 2 places. That's perfection. When x is 75, we're going to do the same thing. So z is equal to, this time x is 75. The mean is still the same. The standard deviation is still the same. Okay, let's figure out what this z-score is. And remember, to 2 places after the decimal, what do you get for your z-score?
1.40.
Yes, 1.40. Very, very nice. Think back to the process that we would take to find the area between 2 z-scores. Again, a normal curve may help. I'm just going to turn this for a moment so that I can draw the curve and show you what's going on here. And here we have it. Okay, we've got 0, 1, 2, 3, -1, -2, -3. We're going to plot these 2 z-scores, -0.60, that's approximately here. Draw your dotted line up. We're going to plot the point 1.40. That's approximately here. Let's draw the dotted line up. And we want to find the probability that your statistics exam score falls between a 65 and a 75. So we want the region between. Please go to your z-score table. And I would love for one of you to tell me, what is the area to the left of a z-score? -0.60. I would like the area to the left, -0.60. Whenever you have it, go ahead and share. Yes, Ava, excellent. Ava says it's going to be 0.27425. That's correct. Let's write that down. 0.27425. Next, flip to the positive side of your table. You're now looking for a z-score of 1.40. You want the area to the left, 1.40. So someone other than Ava, please provide the area to the left.
Can I just say?
Yeah, of course.
So, sorry. Would it be like a 0.8508?
You're almost there. You want to look for where it says 1.4.
Okay, so
And then the first column is 1.40.
0.9.
Yes, keep reading.
0.9192.
Yes, beautiful. 0.9192. Yes, perfection. We want 1.40. So 1.40 is right here at 0.9192. Yes, excellent, excellent, excellent. And then the last thing we have to do to find the area in between is what? We saw this last class. What do we have to do?
Subtract it.
Yes, subtract it. That's it. So we're going to do 0.9192. We're going to subtract 0.27425. Let's punch this into our calculators to make sure that we're getting the same thing. 7425. Good. And what do you get for the area between?
Point 644. Oh wait,
Keep going.
it's around to 4, right? Well, 9, but
You're okay. Keep going.
0.6449, but it rounds up. So
True, it definitely does. So we would have 0.64495, which you could, if you wanted to, 4 places, like for instance, in Lumen, because this 5 makes this 49 go up, that's going to be a 50. So we actually could also say that that's the same as 0.6450. I would accept either answer. Because we have to one more decimal place, we might as well keep the one that's just a little bit more accurate. That's fine by me. But yes, this one would be just as accepted in Lumen. So to write our final answer, we will say that the probability that the statistics exam score is between a 65 and a 75 is and you can write either answer here. I'm going to write 0.64495. Because as always in Lumen, you can round to one place fewer if need be. I love it. What are your questions? What do you think? I'm going to draw the curve and shade the region. That's going to be helpful. Was that easy to follow along? What are your thoughts? Not too bad. I don't have any questions, so hopefully that means everything's okay. Turn the page. One more problem for today. Practice number 4. Women's heights are approximately normally distributed with a mean of 64 inches and a standard deviation of 2.7 inches. This is nice. We're already provided this information, so it may just be helpful to highlight what we have. Boom, there it is. Given this information, answer the following parts. We're going to start with part A. What is the probability that a randomly chosen woman from this population will be between 68 and 71 inches tall? So in other words, I provided to you the actual statement. Find the probability that 68 is less than X, which is less than 71. And that is the height of the woman. Okay, so talk me through the first step. What do we have to do initially?
Find the z-scores.
Yes.
Yeah, so it would be the 68 minus 64 over 2.7 for the
Yes.
first one. And then z also equals the 71 minus 64 over 2.7 and then calculate.
Yes, awesome. That's exactly correct. Notice Jenny says we've got to find the z-scores associated with each raw data value. So we know that X is 68. We also know that X is 71. So we want to find their associated z-scores. So we do X, the raw data value, minus the mean divided by the standard deviation. Go ahead and take your calculators. Thank you. Someone else. What is the first z-score? What's the value of the first one? Shout it out.
1.48.
Yes, excellent. Excellent. And thank you, Nick. I see that in the chat, 1.48. Even though you got this value, remember that z-scores are provided to 2 places after the decimal. So 1.48. Let's do the same thing for the second one. Someone else? When you punch this in?
2.59.
Yeah, 2.59. Excellent. Very, very nice. We're going to go through the same process. Let's draw the curve. We're going to shade the appropriate region. Let's label this. We've got 0, 1, 2, 3. We have our -1, -2, -3. We want to plot 1.48. That's approximately here. Draw your dotted line up. We want to plot 2.59. That's approximately here. Draw your dotted line up. And then, of course, we're going to shade in between. That's what we're looking for. We want to know the probability that that woman will fall within those 2 heights. Let's go to our, actually, you tell me what's next. What do we do? What do we do next? Go ahead and shout it out. Share with the class.
Subtract the area from like the left to the first point.
Yes, so we're going to go to our chart. We're going to look at what is the area to the left of the z-score of 1.48. And what did you all find? What was the area to the left?
Is it 0.9306?
Yes, beautiful. 0.9306. Good. We're going to do the same thing. We want the area to the left of a z-score of 2.59. So Sudhajini gave us to the left of 1.48. Someone else give us to the left of 2.59. Emma, you're
0.9952.
yes, excellent. 0.9952. Beautiful. We know to find the area between, we're going to subtract these values. So 0.9952, that's the larger value, subtract the smaller, right? We want to make sure that our area is positive. 0.9952 minus 0.9306, and that gives us the area of
0.0646.
yeah, awesome. So the probability that a woman who is randomly chosen will have a height that is between 68 and 71 inches tall is 0.0646. So if you were to talk about that using percentages, you'd say there's about a 6.46% chance that that would happen. So it's pretty small. Okay. Beautiful. Excellent work. I am going to stay after to answer any questions you may have. And I actually intend on recording those questions just in case you're working on the homework later and you're like, maybe they went over this. Let's check the video. Besides that, I will see you all. Have a wonderful weekend. I'll see you all on Wednesday.
Thank you.
Have a great
Welcome.
weekend.
Thank you.
Thank you. Have fun in Buffalo.
Good luck.
See ya. Thanks, Donna. All right, so let's take a look at some questions that you have from the homework. Sudhajini, we're going to start with yours. Is that okay? This. That there. All right, let's take a look. Funny, she sits right at the base by the wheels, and I don't want to roll over her. Okay, so Sudhajini, was this from the Unit 5 binomial distribution homework?
Yes.
Okay, perfect. So let me go ahead and share my screen. Let's take a look at this. Binomial distribution. And we want the M&M problem. So let me go to where that is. Here we go. Question number 10. Does that sound good?
Yes.
Okay. According to Master Foods, the company that manufactures M&Ms, 12% are brown, 15% are yellow, et cetera, et cetera. You randomly select 4 peanut M&Ms from an extra large bag of the candy. So this is really important to keep in mind. It also says round all probabilities below to 4 decimal places. So this is really good to know. We want to round it to something like 0.1234. We don't want it to be larger, and we definitely don't want it to be a percentage. So we want to compute the probability that exactly 2 of the 4 M&Ms are blue. So the first thing we do is we say to ourselves, okay, well, what are the chances that the M&M will be blue? So we'll call that the probability of success. So Surajini, what is the probability of success, meaning that we pick a blue M&M? What's that?
No, I didn't answer anything.
Oh, sorry.
Yellow, blue.
And by the way, anyone's
23.
Yes, 23%, which means 0.23. So then what are the chances we don't pick a blue?
Would it be 23, 77?
Yes, that's exactly correct. Okay, so we have the probabilities. Now we want to actually use the formula. So as we know, we're choosing exactly 2. So the formula is going to be 4 choose 2. And I'm going to write this out, by hand, because we don't have the notation here that's fancy. So 4 choose 2, this is the combination part. And then you want the probability of success, which is 0.23. We're going to raise that to the number of successful outcomes. So we want 2 of them to be exactly blue. So raise to the second power. And then we want the rest to be to not be blue. We want those to be failed outcomes. And if 2 out of the 4 are blue, then 2 out of the 4 won't be, right? So there is our that's our equation, that's our formula. So we can do 4 choose 2. We're going to use our calculator to do so. That's going to give us 6. 4 choose 2 is 6. Then we're going to multiply that by 0.23 to the second power, and then times 0.77 to the second power. So we should be getting for our first one 0.1882, because it's looking for 4 places after the decimal and no more than that. Was that one okay, Surajini?
Yes, it was.
So we do 0.1882. And then we can verify that that is exactly correct. So 0.1882, you can kind of see that there. Don't worry about this other stuff. It's just showing what you ended up using to do that through code. So 0.1882 is correct.
Okay.
Okay, so talk me through this next one, Surajini. It says compute the probability that 2 or 3 of the 4 M&Ms are blue. What might you do in this case?
I don't know. I'm going blank here.
Okay, what I am going to do though is I'm going to write this, because I think you may find this helpful. So when we did our previous problem the first part, we wanted to find the probability that exactly 3, wow, not 3, I meant 2, that exactly 2 of the M&Ms are blue. So that's actually the probability that we found, the probability that X is equal to 2, right? The number of M&Ms are blue. And we wanted exactly 2 of them. So if we want to, go for it.
P of X equal 3.
Yes, exactly correct. That's
Okay.
the next one we want to find. The cool thing about this is because we already found X is equal to 2, in order to find X is 2 or 3, what are we going to do with those probabilities? We're just going to add them.
Okay.
Yeah, that's it. If you know the probability of choosing exactly 2 blue M&Ms, and you know the probability of choosing exactly 3 M&Ms, then the probability of choosing 2 or 3 is going to be the sum of both of those. Now remember with this one, we're choosing 3 M&Ms to be blue, which means out of the 4, only 1. Yes, exactly. So we're going to punch this in. 4 choose 3, which is 4. Multiply that by 0.23 to the third power. and then multiply that by 0.77 to the first power, which is just 0.77, and that gives you 0.0375, because we want to 4 places after the decimal. Keep in mind that this is asking for 2 or 3, so we must add these two probabilities. So let's take 0.1882 and add 0.0375. That will give us a total probability of 0.2257.
Okay.
Beautiful.
Question.
Yeah.
So for the one that you're on, I have different numbers.
Yes.
I have 2 and 3. So would the 3 go on top and the 2 go on the bottom?
Yeah, you're going exactly just what your problem states. All I'm doing here is I'm trying to show you the why behind it, so that regardless of what it looks like, you'll be able to do it. You
Okay,
see?
so I would follow the first method, right? For each of them?
Yes, so essentially you're just gonna use your information, just base it on that. Like if it said exactly 3 of the 4, then it's gonna be 4, choose 3, right?
Yeah, and then the 3 would be above 20.23.
Yes, so like here, yes, because you're
Yeah.
choosing 3 to be successful, which means 1 is gonna be not successful.
Okay.
Good. So this idea does not change even when we look at the next examples or the next questions. Compute the probability that at most 2 of the 4 M&Ms are blue. What does at most 2 mean?
It means 2 and everything below.
Yes. Which,
So I'm sorry, I'm going to find a probability of 1 and then the probability of 2 and add those together. And
you're
that's
so close. There's one more you missed. 0.
Oh,
Yes. So we want the probability that X, the number of M&Ms, is at most 2, which
Mhm.
means that's going to be less than or equal to 2. I'm going to write the equal to by hand because of this software, of course. So less than or equal to 2. That means we want the probability when X is 0 plus the probability when X is 1 plus the probability when X is 2. We want all of those. We have one of them already, but we didn't do the 0 or the 1. So those are the ones you'll have to do.
yeah.
A shortcut to this is using that particular website that I shared with you. So I can show you that now if you would like. I know you're good with that, but I can
the
show
cal-
the other ladies in case.
The calculator.
Yeah.
Okay.
Let's look at the calculator. So we know that N, in this case, the total number of M&Ms being chosen are 4. And according to this, at most 2, so it's going to be less than or equal to 2. So let me show you what this looks like when I use the calculator. I'm going to get rid of all this because this is in my way. Let's try that again. Clear all drawings. Thank you. So let's write binomial distribution calculator. Let's use this first one. Perfect. So the probability of success, according to this example, the probability of success is 0.23, right? That's for the blue M&Ms. We know that there are 4 trials because we're choosing 4 M&Ms. We don't know what the outcomes are yet. We're just saying we're choosing 4 M&Ms for sure. Now, according to this, we want to find the probability that at most 2 of the M&Ms are blue. So we're going to write the 2 in here, and then that's all we need before we click calculate. So we're going to go ahead and click calculate. And then I'm going to remind you of the inequality that this is referring to. At most 2 means the probability that X is less than or equal to 2. Let me write the equals in there. So less than or equal to 2. Having said that, when we look at this example, or this page, this gives us the probability that X is exactly 2. That's not what we want. This gives us the probability that X is less than 2. We're getting there. And then this one gives us the probability that x is less than or equal to 2. This is the one we're looking for. We want to match it exactly. So if we look at these, this value, this probability, we have 0.9597, just 4 places, 0.9597. And that's what we want to write here, 0.9597. All right. Let's do one more. Compute the probability that at least 2 of the 4 M&Ms are blue. What does that mean?
2 or more.
2 or more. So we would write that as x is, what would the notation be here if it's 2 or more?
X is less than or equal to 4.
You're close. We want 2 or more. So we want it to be greater than or equal to 2 because it's 2 or greater than that. What will help is when you're deciding, write down the values. So you said 2 or more. If that's the case, then you mean 2, 3, or 4, right? The probability that x is 2, the probability that x is 3, the probability that x is 4. The great thing about the binomial calculator is that we've already inputted 4 trials, 2 successes. So we're looking for the probability that x is greater than or equal to 2. Look through all of these, you'll see that it's at the very bottom. The probability that x is greater than or equal to 2 is 0.2285. We're going to round 0.2285. 0.2285. Excellent.
I have one more question, and probably this will stick with me.
Yeah.
So I'm struggling a little with, and I've always struggled with the signs. So the side that the V is open to, it's open to more, right?
Yes. The other thing too that I'm going to say, doesn't that look like an L?
Yeah.
Right?
I
So-
call it V.
Yeah, right. Well, it kind of looks like an L, so you can say,
Okay.
oh, that's definitely less than. So which means whatever value you place here is going to be less than whatever values on the right. So that implies that the value on the right has to be bigger according to the statement.
And if what I'm thinking, it's getting more here, it's eating more there, it's getting more, right?
So so what if I wrote this? What values am I referring to?
So everything on X is less than 3.
Yeah, exactly. So 0,
Okay.
1, 2, but not including 3. Yes, beautiful. Yeah, exactly. That's perfect.
Okay.
That's perfect. Okay, take a look at, we might as well finish this problem while we're at it. If you repeatedly select random samples of 4 peanut M&Ms, on average, how many do you expect to be blue? Do you see the language that is in this problem? On average, how many do you expect to be blue? That means we need to find the expected value. Does anyone remember the formula for the expected value of a binomial distribution? What is it?
N times P.
Yeah, n times p. Super cool. We know that n is a number of trials, that's 4. And we know the probability of success is 0.23. So let's punch this in. 4 times 0.23, because remember, we're just talking about the blue peanuts. So that's going to give us an expected value of 0.92. Round your answer to 2 decimal places. So on average, we can expect 0.92 blue M&Ms out of every 4 peanuts that we choose, okay? Technically, we don't expect 1, we can get pretty close, but 0.92 is our expectation. So I know that really doesn't have too much of a meaning, but we're gonna write it exactly as is. And what would the standard deviation be? How would you calculate the standard deviation for a binomial distribution?
You square root n times p times q.
Yes, perfect. And I'm going to write that out myself. So we are going to square root n times p times q. We know that n is 4, p is 0.23. So we have 4 times 0.23 times 0.77, that's q, right? And we want the square root of that. So we want the square root of 4 times 0.23 times 0.77. And that's going, and we want to round our answer to 2 places. So you should have 0.84 as your answer.
Confused where you got the N, P, and Q from.
So let's go up a little bit. Because we are randomly selecting 4 peanut M's from a large bag of candies, that tells us the number of trials, which means n is 4. Now, in terms of p is the probability we choose a blue M&M. The chances of picking blue are 23%. So 0.23 is a probability we choose blue. Well, the probability we don't is what's left over.
Oh, okay.
Good. Excellent. Excellent. Any other questions on this problem?
My question is different, so it's kind of confusing going back and forth.
Yeah, which is actually, I would recommend not going back and forth because of that. It takes away from your opportunity of like kind of, you know, absorbing the information. But the good thing is we have it here on video, so you could always take a look at the video again if you needed to kind of reference what we did together here.
Yeah.
Perfect. Perfect.
I have a question about range rule of thumb.
Yes,
the minimum and maximum.
this stuff. Go for it.
I'm not sure what question it was on, but it was in the binomial distribution.
Okay.
It's one of those questions.
Oh, like this one.
Yeah.
Okay, perfect. So let's just do number 11 so we can take a look at the range rule of thumb. So assume that a procedure yields a binomial distribution with n is 643 trials, and the probability of success for one trial is 0.79. So Nicole, what's the probability of failure in this case?
Hold on, I can't do math that right.
That's okay.
0.21.
Perfect. So we have the probability of failure. The first thing we want to do is find the mean for the binomial distribution. The mean is the same as the expected value, and we know that that's found by taking n and multiplying it by q, or n times p, sorry. So the mean is n times p. Remember, that's the same as expected value. So 643 times 0.79. What does that give us? Let's punch this in. And it says round answer to 1 decimal place. So what would you say in this case?
508.0.
Yeah, I would too. 508.0. I'm going to write here for everyone watching the video that when we punch this in, it gave us 507.97. And if we wanted to round to 1 place after the decimal, that's going to go up, which means the whole number is going to go up. Good. All right, so we're going to find the standard deviation, which is the square root of n times p times q. So I'm going to write this in here. The square root, sorry, that looks like craziness. So the square root of 643 times 0.79 times 0.21. We want to round this answer to 2 places after the decimal. And in the calculator, I get this. 10.32829608. 2 places after the decimal tells us that we are going to write 10.33 as my standard deviation. Now, here comes the range rule of thumb, Nicole. If we want to find the lower value, we're going to take the mean and subtract twice the standard deviation. So that'll give us our minimum. And then the maximum is the mean plus 2 times the standard deviation. So let's figure out the min first. So we have, and we're going to use the values that we inputted into Lumen. So 508.0 minus 2 times the standard deviation, which is 10.33. So let's figure out what this gives us. So 508 0.0 minus 2 times 10.33. I find that my minimum value, my minimum usual value is 487.34. Let's do the maximum. So it's the same thing, 508.0, but this time it's plus 2 times the standard deviation. And let's go ahead and punch this in. And we get 528.66. Good. Now I'm going to write the range rule of thumb using the interval notation that we have written in our classes. So 487.34, comma, 528.66. Okay. Nicole, looking at just this interval, what is the whole number that is right outside of this interval? What's the whole number that's closest to the smallest value, but it's outside of the interval?
487.
Okay, so I'm going to write 487 right here. So that's not in the interval, right? It's outside of it. It's below it. What's right outside this one?
529.
Perfect. Okay. So what that means is those are unusual values. What this is asking us for is enter answer as an interval using square brackets, which means we can include them, but only with whole numbers. So we want the usual values, which means we want to be inside this range. We see that 487 is smaller than the smallest value in the range. So that means 488 is going to be the value that we're going to use for our lowest included value. So brackets, we're going to do 488, not 487, okay, because that's to the left of the range, that's outside of it. And then what's the highest value that we are going to include?
528.
Yes, perfect. 528 is inside this range. It's the whole number within this range. So we know that we are correct in stating that. Okay, so you want to make sure that your values are inside that range that we calculated.
I was getting confused on the minimum one because
Yeah.
it just the whole number thing.
Yes, because you're thinking, why can't I say 487? But
Because
yeah, because it's outside of that range. It's below it. It's not inside.
it's a partial of a whole. Like
Yes.
the 0.4.
Yes, so you want to make sure you finish that. So your 487, that's in the range. 488 is in the range, 487 is not. Good.
Okay. I had another question, but I don't know if anybody else wanted to go first.
Sure. Anyone? Stephanie? Oh, Emma?
I can wait till after. You can go, Nicole.
Okay.
Okay.
This was about the Unit 5 application homework, actually,
Yes.
on question 4.
Okay.
I know we haven't gotten our probabilities yet, and I have to redo my question.
Let's take a look. And I'll open this up. Perfect. Yes.
Number 4. I'm confused on what it's asking.
Well, when it's saying what is the probability that more than 7/8 of your class responded? Yes. I want you to start thinking about what part of the class that represents, right? 7/8 of the class. I want you to think of how many students that would actually be. Okay.
I don't know
it's-
yet.
Right. And that's okay. That's okay.
I don't even know.
So all you have to do in this case is, and I'll give you an example because I don't want to tell you exactly, but if I said, you know, what is the probability that more than half of your class responded? Yes. If you had 26 respondents, then you're basically saying, what is the probability that more than 13 of your class responded? Yes, because that's half of them, right?
Mhm.
So we're going to do the same idea, except this time it's 7/8. The reason that we picked that particular fraction is because we wanted to make sure that it was a larger number where it was easy to calculate the probabilities above that. Your goal is to collect 25 to 30 responses. So as soon as you hit 25 or more, you can close your survey and then you can take that data and analyze it. Okay. And then think about what is 7/8 of the total number of responses that you had. That's going to give you that value. You want the probability that more than that responded yes.
You multiply them together? Okay, I was confused on how to even get that answer. So if it's like 25, you multiply by 7 divided by 8?
Yeah, it's like if I wanted 3/4 of 30, let's try writing it correctly. I will literally do 3/4
Oh yeah, all
times.
we need is multiply it though.
Yeah, exactly, exactly. Good.
So if it's like a partial number, then how would we round it?
That's up to you and you can justify that.
Okay,
So I would if you were doing that. So you would say 7/8 of, whatever is 20, 5.3. So I decided that means I am only including 25 responses, right? That kind of thing as saying
Yeah.
yes. So you're finding the probability of that or more.
oh wait, probability that more responded yes. So it has to be within the yes ranges then?
So first you figure out what that value is, and then you want the probability that more than that responded yes.
So it's still taking the whole and multiplying it by 7/8.
Yeah.
So the whole total number of trials
Total number of trials,
Multiply.
yes,
divided, okay,
always, because you want to base it on the total number of responses that you had.
okay.
The
More than-
binomial distribution formula will give you the probability. So you're just focused on how many
I
students.
think I'm confused on the yes part, responded yes,
Think of yes as just being a success, and you know the probability of success.
Okay,
Good. So we're going to go through the same way we did the binomial distribution problems just now in Lumen. And then you'll say, n choose this many, the probability of success raised to that many, and then the probability of failure raised to the rest, that kind of thing.
that's for like 3 and then like 5, basically?
Yeah, 3, 4, and 5, yes.
Oh, so we do that calculation for 4 as well?
Yeah, oh yeah.
So
You
choose.
just-
Oh, okay.
You just have to figure out more than how many students. So what is the probability that exactly 5 responded yes? So it's n choose 5,
Mhm.
right? What is the probability that more than 7/8 of your class responded yes? Well, it's going to be n choose and then whatever 7/8 of that number is, right?
Which is what you get from multiplying
Yes.
that by the total
That-
number. Okay.
Yes.
I got
Beautiful.
Okay.
Perfect.
I'm still a little confused on number 4.
If I had, let's play a game.
Okay.
If I told you, I would like you to find the probability that more than 5/6 of the class said yes, and you had 28 responses. How many people are you looking for? You'll need your calculator, of course. How many did you guess, Stephanie?
I don't have my calculator. Let me see where it is.
Okay. And anyone else can help too.
23.3333.
Good. So Stephanie, we've got it covered. So 5/6 of 28 is 23.333. So where it says 7/8 of your class, we're going to replace that by saying probability that more than, what would you write? 23? We'd probably write 23, right?
So you got that number by multiplying the 5 out of 6 times 28?
Yes.
Okay.
So we replace that phrase 7/8 of your class or 5/6 of 28 with probability that more than 23 responded yes.
Okay.
So it can't be like a partial number when we do the whole n choose thing.
Right, you want to choose a total number of students, so that's why we would either round down or round up.
Okay.
Good. You're not going to choose 0.3 of a person. So make sure that that value is rounded. Just like you said, what if it's a fraction of a person? Well, you round. So I would round down because I know 23 people said yes, exactly. 0.33, maybe in my mind, that means that they're still thinking. Okay, and they haven't thought about what they want to say yes, or what they want to say. So we would just choose 23 responded yes. So what is the probability that more than 23 responded yes? Now, if you have 28 students, that means you want to find the probability, it says more than 23. So you want to find the probability of 24, 25, 26, 27, and 28, and you want to add those up.
So do you recommend doing that by hand? And
I mean, I would at least do 3 by hand and 5 by hand. But if 4 ends up being like a lot, in this case, we had 5 different calculations, I would just use a binomial calculator.
okay. Can you go through how that works again with like this one, for example?
Yeah, for sure. Let's say that in this case, we see that n is 28, right?
Mhm.
And our number of successful outcomes is 23. So we're essentially, and by the way, the probability of success, let's say according to your question, you found that there was a 65% chance that everyone will say yes, which means that there's a 35% chance that they say no. So because we want the probability that more than 23 responded yes, we want the probability that X is greater than 23. Would you agree with that?
Yeah.
Okay, let's punch it in. So I'm going to close this. We want to change these values. So the probability of success on a single trial we're saying is 0.65. The number of trials, the number of students, 28. The number of successes, 23. Let's go ahead and calculate this. And then we want the probability that X is greater than 23. So that's going to be right here. X is greater than 23. And you would say that the likelihood is 0.0136.
Okay, so round to 4 decimal places.
Yeah, that would be a good idea.
So
Okay.
this is for number 4 or which one?
Let's look back and you tell me.
Okay.
What do you think?
Number 4.
Definitely. We are finding the probability that more than a certain number responded yes, so it has to be number 4, because essentially we're looking at the probability of 24, 25, 26, and 27, 28. Instead of calculating all 5 by hand, we could just use a binomial calculator. We just have to pick the correct one. If it says X is greater than 23, we want to make sure that we click the one that has that inequality. So the probability that X is greater than the number of successes, which is 23.
So it's
Okay.
okay, we don't show our work like for all of the steps for each one, like
Right.
24, 25, 26.
Yeah, exactly. I would say, I would make a comment. I use a binomial calculator to compute the following probability. I would include that probability statement. Probability of X is greater than 23 equals, and then I'd write the solution there.
Okay.
Good.
So N is the number of students total,
Yeah.
and then X is the number that said yes.
Yes.
Okay.
Your number of successes, how many you want to say yes. So just like with the previous one, what is the probability that exactly 5 people responded yes? So you know what N is, because it's the total number of students who responded to your survey, and you want to choose exactly 5. So N choose 5.
Okay.
Good.
Where'd you get the 65 from?
Oh,
Sorry.
we were just kind of playing around with ideas. So I said,
Okay.
maybe when Nicole collects all her data, she might get a probability of success of 0.65. Who knows?
Okay, so that's like the number of people that said yes divided by the total.
Yes. Beautiful.
Okay,
That is correct. Nice.
thank you.
You're
I
welcome.
have a couple questions if that's okay.
Yes, I only have, I have less than 10 minutes because I teach at 11, but go for it.
Okay. My questions were for number 6. I think the K factor just really confused me.
Is it binomial distribution?
Yes.
All right, so number 6. Let's take a look. This one. Perfect. So
Yes.
assume that a procedure yields a binomial distribution with a trial repeated n equals 14 times. Use either the binomial probability formula or technology to find the probability of k equals 6 successes given the probability that p 0.34 of success on a single trial. So we're going to do the same thing. Do you agree here that even though this says probability of x is equal to k, what is k?
6.
Yeah. So we just want to find the probability that x is equal to 6. Okay.
Oh, okay.
And then we just use the formula.
Okay, gotcha.
Okay.
And then one really quick question, I'm sorry.
That's okay.
For number 9, I am really comfortable with the min and max finding everything with that, but for some reason, I don't know if it was the sensible whole numbers that confused me, but every time I've done this, I've tried like so many times, it's just incorrect.
What was your minimum value?
Well, my question just restarted. I think I have a picture of it. I don't know.
Oh, okay. Because I was gonna say, let me throw some ideas out there. What if you ended up with usual values of 32.13 and then all the way up to 45.56? And they wanted you to find the usual number of yellow eggs. So what's the smallest number of usual values?
The smallest would be 33.
Yes, 33 is correct. And what's the largest?
45.
Yes, that would be your answer. So you want to make sure that the values you choose are within the range. And I think if you do that again, you're going to have, it's going to be much better.
Okay, I'll try. Thank you.
Good. You're very welcome.
One more question. When we're computing the probability of like success for the homework, if it's like a 0.4642, I just use an example. Do we round just 2 decimal places?
Yes, I would, only because all of our binomial distribution problems have 2 places after the decimal for P and Q.
Okay, thank you so much.
You're very welcome. Excellent. I will see you all on Wednesday. Have a great rest of your week.
You too. Thank you.
Bye-bye.
Bye. You're welcome.